In this section, we'll explore the fundamental concepts of how cameras work. At its core, a camera is a device that captures light and converts it into an image. All cameras, from smartphones to professional DSLRs to traditional film cameras, share the same basic principles. Let's look at the key components found in most cameras. These include the lens, aperture, shutter, and image sensor or film. Let's look at the key components found in most cameras. These include the lens, aperture, shutter, and image sensor or film. In the following sections, we'll explore the step-by-step process of how light becomes a photograph. Now let's delve deeper into the role of light in photography. Photography literally means drawing with light. The term comes from the Greek words photo, meaning light, and graphy, meaning drawing or writing. Light is the fundamental element of all photography. Without light, creating images would be impossible. Let's visualize how light creates photographs. First, we need a light source, like the sun or a lamp. The light travels through space until it encounters an object. When light hits an object, some of it is absorbed and some is reflected. The reflected light carries information about the object's color, texture, and shape. Light rays travel from the source in all directions. Some of these rays strike our object. The object reflects these rays, carrying information about its appearance to the camera. The light reflected from an object carries important visual information. This includes the object's color, which comes from different wavelengths of light. It also reveals texture by how the light scatters on surfaces. The shape is defined by how light creates edges and shadows. And finally, intensity shows us the brightness levels. Different lighting conditions create dramatically different photographic results. Hard light creates strong, defined shadows with high contrast. Soft light creates diffused, gentle shadows that wrap around the subject, creating a more flattering look. Backlighting creates silhouettes and rim lighting, highlighting the edges of subjects. The quality, direction, and intensity of light dramatically affect the final image. Understanding and controlling light is the essence of photography. As we've seen, without light, photography would be impossible. It is the essential element that makes all image creation possible. Camera lenses are sophisticated optical systems designed to gather and focus light. A lens contains multiple glass elements that bend or refract light rays. In a convex lens, the light rays converge at a point called the focal point. Modern camera lenses are made up of multiple glass elements. Each element has a specific purpose, such as gathering light, correcting optical aberrations, or focusing the image. Focusing a camera involves adjusting the position of the lens elements relative to the image sensor. This changes where the light rays converge. The quality and design of camera lenses significantly affect the final image. Key factors include sharpness, distortion, chromatic aberration, contrast, and flare resistance. Understanding how lenses work helps photographers choose the right equipment for their specific needs. The aperture is an adjustable opening in a camera that controls how much light enters. When the aperture is wide open, more light passes through. As it closes, less light enters the camera. Aperture size is measured using f-stops. The f-stop is the ratio of the lens's focal length to the diameter of the aperture. Smaller f-stop numbers like f1.4 represent larger aperture openings, while larger numbers like f22 indicate smaller openings. Aperture size dramatically affects depth of field, which is the range of distance that appears in focus. A wide aperture with a low f number like f2.8 creates a shallow depth of field. The subject is in focus, but the background is blurry. A narrow aperture with a high f number like f16 creates a deep depth of field, keeping more of the scene in focus. The iris mechanism consists of overlapping blades that expand and contract to change the aperture size. As the blades move, they form a nearly circular opening that can be adjusted to precise diameters. The camera shutter works like a door that controls how long light reaches the sensor. The shutter sits between the lens and the sensor, blocking light until it opens. When you press the camera button, the shutter opens for a precise amount of time, allowing light to reach the sensor. Shutter speed is measured in seconds or fractions of a second. Common shutter speeds range from extremely fast, like 1,000th of a second, to very slow, like 1 full second or longer. The shutter speed you choose has a significant impact on how motion is captured in your photos. Fast shutter speeds, like 1,000th of a second, freeze action. The subject appears sharp and crisp with no motion blur. Slow shutter speeds, like 1/15th of a second, create motion blur. Moving subjects appear streaked or blurred across the frame. There are different types of shutters used in cameras. The most common in DSLRs is the mechanical focal plane shutter. This type uses two curtains that move across the sensor. When taking a photo, the first curtain moves away, exposing the sensor. After the desired exposure time, the second curtain follows, covering the sensor again. For fast shutter speeds, the second curtain begins to close before the first curtain fully opens, creating a moving slit that exposes different parts of the sensor in sequence. Many modern cameras also use electronic shutters, which have no moving parts. Instead, they control exposure by electronically activating and deactivating the sensor pixels. Understanding shutter speed is crucial for capturing the right amount of motion in your photographs. The image sensor is the heart of any digital camera. The image sensor serves as the digital equivalent of film in traditional cameras. It contains millions of light-sensitive photosites, commonly known as pixels, arranged in a precise grid pattern. Each photosite functions as a light detector that converts incoming light into an electrical signal. The intensity of the light determines the strength of the electrical signal, which translates to the brightness of that pixel in the final image. There are two main types of image sensors used in digital cameras, CCD and CMOS. CCD sensors offer excellent image quality with lower noise but consume more power. CMOS sensors are more energy efficient, process data faster, and are more economical to manufacture. Sensor size significantly affects image quality. Larger sensors can capture more light. The larger the sensor, the better it performs in low light conditions with less noise. It also allows for higher resolution images with more detail. The image sensor, with its millions of tiny photosites, is truly the heart of any digital camera, converting light into the digital data that becomes your photograph. Understanding how the image sensor works is key to appreciating the technology behind every digital photograph. When a digital camera captures a color image, it faces a fundamental challenge. Most camera sensors can only detect brightness, not color. To capture color, a special filter array is placed over the sensor, the Bayer filter. This filter consists of a pattern of red, green, and blue filters arranged in a specific order. The pattern has twice as many green filters as red or blue, because the human eye is more sensitive to green light. Each individual photosite on the sensor captures light through just one color filter. This means that each photosite only records one of the three primary colors, red, green, or blue. The other color information at that location is not captured directly. Since each photosite only captures one color, the camera's processor must calculate the missing color information through a process called demosaicing. Demosaicing algorithms analyze neighboring pixels to interpolate the missing color values. For example, a red photosite would get its green and blue values calculated from adjacent pixels. This process is applied across the entire image, creating a full RGB value for every pixel. After demosaicing, the camera has effectively created three separate color channels, red, green, and blue. These three channels are combined to create the final full-color image we see. Through this color capture process, digital cameras can recreate the full-color world we see. After image processing, the camera must store data in specific file formats. The two most common formats are JPEG and RAW. Let's compare them. Image compression is a key factor in determining file size and quality. Raw files store all the data captured by the sensor without compression, resulting in large file sizes but preserving all details. JPEG compression reduces file size by selectively discarding some image data, particularly in areas where changes are less noticeable to the human eye. Modern cameras store images on either removable memory cards or internal storage. SD and CF cards are removable storage media with capacities ranging from 16 gigabytes to 2 terabytes. Many newer cameras also feature internal storage, which offers faster write speeds but cannot be removed. Along with the image itself, cameras also store metadata, which provides valuable information about how and when the photo was taken. This metadata, often called EXIF data, includes camera settings, date and time, GPS coordinates, and many other details. Let's examine the complete data pathway from the image sensor to permanent storage. The journey begins at the image sensor, which captures light and converts it to an electrical signal. This analog signal is converted to digital data by the analog to digital converter. Next, the image processor applies algorithms for color correction, noise reduction, and other enhancements. The processed data moves to the buffer memory, allowing the camera to handle multiple images in quick succession. From there, the storage controller manages how the data is written to permanent storage. Finally, the image data and its metadata are written to the memory card or internal storage, ready for viewing or transfer to other devices.
Throughout the history of photography, camera technology has evolved tremendously. Yet despite these technological advances, the fundamental principles of photography have remained remarkably consistent. Let's explore how cameras have evolved over time, from the earliest camera obscura to today's AI-powered systems. The camera obscura used the same basic optical principles that today's most advanced cameras still rely on. Light passes through an opening, projects an image, and that image is recorded. Modern computational photography adds layers of technology, multiple lenses, sensors, and artificial intelligence that processes the image data to overcome physical limitations. Today's smartphone cameras are marvels of miniaturization. They use multiple lens systems and AI to compensate for their small size. Despite these technological advances, understanding the basic principles of photography remains essential for taking great photos. Whether you're using a modern smartphone or a traditional camera, the same principles of light, exposure, and composition are the foundation of great photography.